All right, so this is an explanation of the exam, final exam from last semester. I'm going to go over the instruction a little bit because it's going to be a little bit different for your exam. So first of all, the exam time is going to be not the same because last semester this was a full semester class and not a summer session. For summer session classes, the final exam is conducted on the last day of class meeting and also using the same schedule as the original synchronous scheduled time. So our time is going to be from 5:30 to 7:30 on the last day of this class, which is let's see, it's on Thursday. And let me just make sure about the date. So that would be tomorrow, which is the 29th. All right, so that part has to be different. The rest of this is almost the same, except for there's no Jonathan's integrated assembler simulator tracer, um, because I have not, verified that program to be working, so I cannot recommend it. You can, however, use the assembler. You can use the simulator, and the trace analyzer is now integrated into the assembler. So you can use all of those. You can use a C compiler. You can use a C debugger, that sort of stuff. Okay. Pretty much the only thing that I do not want people to do, or I, absolutely cannot let people do, is to collaborate. So that is that. Um, and there are comments that are needed. So you need to let me know that you understand the concepts. Alright, so the first part of the file is a C program. So this is not something that you have not seen before, except instead of having two pointers to other struct nodes, this time we have three as an array. And the code is down here. Okay, let me go to the right pane. So this is the C code, and the subroutine that you need to implement is SD insert. Actually, it's already implemented. Okay, the entire program is implemented. The question is it implemented correctly or not? So you have to identify the problems and let me know, what problem that you have identified and how you propose to fix it. And there are some restrictions here, like do not copy and paste. And if you cannot use an external editor, so all the editing must be done in document in Google Doc. So now we look through the code on the left hand side. This is the code in C/C++. So we'll start at the very beginning of the C program, and now we get to the very beginning of the assembly code on the right hand side. There we go. So we have a macro, a fan out, which is defined to be 3, and the intention was to use fan out here to refer to the macro, but I forgot. I forgot that I had a macro called fan out. So when we check the definition of the labels corresponding to the offset to each member, V is still the first item in the structure, but P has 3 items. So the offset to P is correct, but the size of the node is no longer correct because we need to put a 3 here. The original idea was to use fan out, the same as this label name here, but since I forgot to do that in the C code, I could not ask people to do the same in the assembly code. So that's why a 3 is good, even though originally the intention is to use fan out here. But I'm going to keep a 3 so that the assembly code and the C code stay consistent. Then we have the usual no op jmp to main, just to get around the code because I want to preserve the order of the definitions. So you can see we have struct node n6, and it is not initialized in C, and as a result in the assembly code they are all zeros. Now you might say, but that's initialized, but that's, I cannot do anything else. There's no other way to reserve 4 bytes in assembly language without um, specifying the value of those bytes. N5 is initialized, but it is all zeros, so that's how we initialize N5. N4, same thing, they're all zeros. N3, they're all zeros. And then N2 has N5 being the first element of the array P, and that's why we have N5 over here. And then for N1, it has 0 for V, and then N2, N3, N4, the addresses of N2, N3, and N4 are all here, and that's why N1 in assembly language is defined as this. So far, I think we're good. So now we get into SD insert. So with SD insert, as usual, I define the labels first, and then I make references to those labels later. We have one local variable I, so in the call frame, it should have the lowest address after the allocation, so it should be where the stack pointer should be pointing to. LVS is local variable size, and it is defined to be the last local variable and then the size of the last local variable plus. So this way I can figure out how many bytes I need to allocate for local variables. And this calculation here is correct because I is an 1 byte kind of thing. And then we have the parameters, which is n is the first parameter, which should be there should be 1 byte between the last local variable or the local variable that has the highest address and n. So when I define n, I use sd insert underscore lvs 1 plus, and that is correct. Let me check. Yes, so that is correct because this one here is accounting for the return address that is also sitting on the stack. And then we have new node, which is insert and 1 plus, and that is correct because n is a 1 byte integer. And then we have point, which is the third parameter, and that is new node 1 plus, and that is correct as well because new node is a pointer, and all pointers are 8-bit wide or 1 byte wide in the in TTP ASM. So everything is good up to this point. Now we allocate for local variables. So since I already use a label to indicate the number of bytes to allocate for local variables, might as well just use that. But I made a mistake of using add instead of delete. Not delete. Subtract. So we are supposed to subtract, okay, to decrease the stack pointer to allocate. So this one needs to be changed. So I'm gonna put a comment here and say add instead of sub to allocate. There we go. And then we move on to the next statement. So once we have allocated register D, the stack pointer should point to local variable I already. So at that point, all the labels should be effective, should be usable. All right, so now we have, let me just turn on line numbers because I think that should help. At least I can refer to which line on the left hand side. All right, so the first thing we need to do is to check whether n is 0 or not. So we need to offset address, and we're comparing the address. So we are missing an LDBB in this case. Okay, so we need to get to value of n. So I'm gonna put in some additional comment here, just so that I can remind myself how I have changed the program from what it was before. So we're and bb jzi to else, okay, and that would not be correct because in the original C code, okay, let's take a look at the original C code. So in the original C code, when n does equal to 0, we go to the then case and not the else case. So that means in assembly code, we now have to change that. And that also need to be changed. So the when n is 0, we're supposed to go to the then case, and when n is not 0, we're supposed to go to the else case. There we go. All right, so now this is corresponding to the then case, which is line 46 to line 54. And you are more than welcome to insert your own comments here. So if you want to just kind of specify this is from line 46 to line 54. I mean that's probably good to remind ourselves, what, where the assembly code is supposed to be corresponding to in the C code. All right, so next thing we need to do is to check whether point is pointing to something that is null in the C code. So we need to get the offset address, and this is the value of point. Okay, so we can A is point. So I would add, comments like that, in order to keep track of, which register has what. Um, since I cannot keep track of, registers in, what each one has, um, when I see a program where they identify places where changes are needed and there are no comments, I get very suspicious. Okay, so um, hint, the hint here is you probably need to keep track of, use comments to keep track of, which register has what. All right, so the next line is an AND AA, okay, which means we are checking whether something is 0 or not using a JZI that is after that. But what I'm checking is the pointer itself. But the code here is supposed to check the dereference of point. So I am missing a dereference before the AND AA, so I'm going to use LDA A over here. All right, so why not B? Because B is probably used for something else later on, so I'm going to keep B around. And here's LDA0, which is actually how we specify the return value of 0. And the conditional branch here says, JZI to then, which is the then branch of the then branch of, this subroutine here. And the logic is correct. Okay, there's no problem with using an LDI instruction between the and the JZI, because LDI does not change the flags in the ALU. So there's no problem with putting LDI A0 here to pre-initialize the return value, and then we just put something else into register A if we need to. So this logic here is actually fine. JMPI, which means if whatever point is pointing to is not 0, because we do not do, because in that case the processor would not do the JZI to the then label. So this one is correct as long as end if is at the right place. So end if is here, that is at the right place. Although I can spot right here that since at the end of the uh, then branch of the outer conditional statement, there should be a jump around the else of the outer conditional statement. So we need a JMPI to SD insert and if here. The label is already defined down there somewhere, right here. It's just that we need to make use of it. So that's that. All right, so now we get back to um, the then branch of the nested conditional statement of the then branch of the outer conditional statement. So now we are tracking line 48. Line 48 needs to get the value of new node. So we have the offset, we got the address, now we get the value. Okay, looks right to me. And here is why register B is not modified, because I'm going to store that to where B is pointing to. So I need to make sure that register B has the address, has the value of point, because we are storing to what point is pointing to. And this would not be correct because what this is going to store is storing to point as the parameter. So this STBA is incorrect. So that means in this code here, and you want to make the minimum amount of changes, and that's why in the original code, um, it's probably a better idea to do LDBB first, like that, so that B is point, and then A becomes whatever point points to, and that is what we need to check to see whether we to check for 0 in order to determine whether we should go for the then branch or the else branch. So that is the change. Okay, so this is inserted. This is new code. This is also, oh, this is changed. No, I didn't change that, did I? No, I did add this. Okay, so this is added. There we go. So even if you don't comment, like this, I can still grade it. Okay, it's because I got tools to do it. Um, but if you don't do it, you might easily lose track of what the original program looked like. So over here, unless you track things like this, unless you know that B is the value of point as a parameter, it is pretty difficult to find out, whether this is going to work or not. And then we specify the return value of 1, which is corresponding to line 49. And then we then go to, that's the end of the end if of this entire conditional statement, because the else is done over here. So it's not, so it's actually being done, but it is done in a very strange way. So when this is all done, we need to get out because we don't want to fall through to the else statement, and that's why we have the unconditional branch to sd insert underscore end if. All right, so now our focus can be down to the else statement. So the else statement is corresponding to lines, I would say 58 to 63. Okay. All right, so the first thing we need to do is to store a 0 into I. So we have the offset, we got the address, and then we have the A becomes 0, and then it's stored into whatever B points to. So that is indeed going to initialize I. And now we have a loop. So for the loop, I personally like to check the structure first, which is a little bit harder now because the program is kind of long, and I'm using a large font, which makes it kind of difficult to see the entire length of the program. I suppose I can use a smaller font, and then so we can see the entire thing. So I'm looking for the while end, label. Um, Alright, so here is the while end, and right before the while end, we have a JMPI to the while begin, and that is correct, okay, because we need to get back to the original one. So the overall structure of the loop looks okay. So now we need to check the condition. So we in the C code, this is on line 59. There are two conditions. The first one is just a comparison, and then the second one is to check the return value of a recursive call to SD insert. So we're just gonna have to do this one step at a time. The first thing to do is to check the code that checks whether I is less than fan out or not. All right, so we load the offset into register B, and then we load the constant of 3 into register A, and then we do the compare. That is not going to work because we are not supposed to be checking the offset. We're supposed to be checking the value of local variable I in this case. So we are missing like 2 instructions because we need to get to the address, and I'm gonna put added here. And we also need to do a dereference so that we turn the address into the value of local variable I. So now we do the compare. The question is the direction of the compare correct, and am I using the right conditional branch to perform this operation? All right, so we have to find out, what the conditional branches are doing and which one we should be using, because we need to see if I is less than fan out. Um, and if I is indeed less than fan out, then we have a second condition to check. So the compare order here is actually flipped in this case because in this case we'll be checking whether 3 is less than um, I and not the other way around. So this needs to be changed. So B should go here, A should go here. So this one is changed. There we go. Um, and then we double check, make sure that if B, which is I, is less than 3, then we go to while cond 2. So while cond 2 as a condition is a label is defined right here. So we're just skipping over the JMPI to the end of the while loop because if this condition fails, if the JCI fails, that means B is not less than A in an unsigned sense. And let me check the signedness too because I is unsigned. Okay, so that is correct. So JCI is the right one to use. So this logic here looks right to me. And then now we get to the second condition, which is checking whether the return value of the recursive call to SD insert is 0 or not. So I know this looks like a mess, okay, but we do this once again, one step at a time. So the first thing we need to do is to push this on the stack because we are getting a call. Now, I know this also looks really kind of nasty, but once again, we do it one step at a time, starting at the most nested thing, which is getting to point first. All right, so when we get to point, we are also trying to get to, because point is pointing to a pointer, and we are dereferencing that pointer to get to the member called P of the structure that is pointed to by a pointer that in return is pointed to by point. That is really important because you need to know how to read C code, and that's why CISP360 is a prerequisite of this class. All right, so tracking what we are doing with point, we can see that adding node p here is probably not a good idea because it's way too early to add the offset to the member because in SD insert point is really the offset on the stack to get to point itself. So I'm going to comment this out and just say this is changed, and to remind myself that I have to account for node p somewhere. So I'm going to put a to do here and to remind myself. Um, the code syntax highlighting is not on because the file is a txt file. So let me get out and change the extension to ttp-asm so that way I can um, turn on the syntax highlighting, which I think is going to be helpful. So it's in the parent folder fxw. Okay, so we'll change it to fx-w00068887 dot ttpasm. Okay, and then we'll do the nvim again. I have an appointment in about 40 minutes, so I think I got enough time to finish the discussion of the answer. If not, I'm gonna have to break this up into two halves and turn in the first half as soon as it's done, and then turn in the second half when I need to, when I have time. All right, so let's go here, and then I'm just gonna put some comments here. Um, so we'll say A is the address of point at its time, A is point at its time, and then A is whatever point points to at this time. All right, so that means at this point, register A is corresponding to this thing here. And what we need to do, and that thing, okay, this entire thing is a pointer itself. In other words, A is a pointer. It's pointing to a structure. We're supposed to access member P of that structure. So that means we need to, now is a good time to add the offset to register A. So we'll do LDI B, pick some other register, SD insert underscore P. Oh, sorry, I forgot. This is a node, okay, so the offset is node underscore P, and then we add B to A at this point. So now A is the address of this thing here, which is an array. So we are getting to the beginning of an array at this point. And then we're using I as an index, so we need to get the value of I first. So now we have, so this would be incorrect because I'm just adding the offset to get to I to the beginning of P, which is not correct because I really want to add the value of I. So that means there are two more steps here to do. Okay, this is added, and then we also need to add an LDE B, so that now B is the value of I, and then we can add I to register A at this point, because register A already is at the beginning of the P member of the structure that is pointed to by the pointer that in return is pointed to by point. Yes, that you can rewind this and listen to that again. But the point is, A is the beginning of an entire array. By adding I to A, register A, now I have the address of a particular element, which is the one that I need to access. Um, so at this point, A is the address of element I of the array P, which is a member of the structure that is pointed to by the pointer that in return is pointed to by point as a parameter. So we got A at the right place now. Let's see. And I think I got the order flipped maybe because it wants to push B on the stack, decrement D, and then we push B on the stack. So we can change this B to A, or we can change A, add AB to add BA. Either way works because I don't think there are any additional references to A, assuming the value has not changed. Yeah, there are no additional references to A, so it's safe to change add AB to add BA, so we can preserve this one here. So that would push this one single item onto the stack. Next, we need to push new node, and having a 1 plus here is correct because we already push one argument on the stack. So everything, so all the labels representing offset to individual items on the stack, they're now 1 byte off. Okay, so having this 1 plus, to apply to the label corresponding to the offset is the right thing to do. Then we compute the address, then we compute the value. So new node is indeed computed correctly. It is now pushed on the stack, and n is 2 bytes off because we got two items pushed already at this point. We compute the address, we retrieve the value, and then we have to decrement by 1 because it is supposed to push n minus 1 on the stack, and that's why we have to decrement b once. And then we do a decrement d and an stbd. That looks right because now we have just pushed n minus 1 on the stack. Now we push the return address. Okay, that looks right. ldb.6 plus, that's the return address. Decrement d stdb. Okay, so we just push the return address on the stack, and then we do the jump on the unconditional jump to the beginning of the subroutine that we're calling, which turns out to be the same one that we're in right now. And then we have increment d, and we're missing one increment d because we are supposed to have 3 arguments and all 3 need to be deallocated. So I'm going to put one here and say this is added. And then the return value is put into register A, and that's what we are checking because we want to see if it is also 0. If it is 0, we get into the loop. If it is not 0, we get out of the loop. All right, so a 0 goes to the end of this loop. Now that is incorrect. So we need to flip these two, and this one needs to go to the end. In other words, if the return value is non-zero, then we want to get out of the loop, because to stay in the loop, we want the return value to be 0. That's why JZI goes to the body, JMPI right after that goes to the end of the loop. So inside the loop, we're supposed to increment the local variable I. We got the offset, we got the address, we got the value into register A. We add 1 to the value, and then we store the value back into um, I, because B is the address of I. So when we store in dereference to B, we are storing into local variable I. That looks right to me. And then we have a JMPI to the beginning of the loop. That looks right. And at the end, okay, this is the end of the subroutine. Let's see. Yeah, okay, so that's the end of the subroutine. Oh, this is specifying the return value. So after this loop, we have to use the return value, which is the negation, the logical negation of I does equal to fan out. So we have to compare. Um, there are several ways to do this. This is the easiest way. We got the offset, we got the address, we got the value, we got the constant that we're supposed to compare to. This is the compare. And just like before, I used the trick of initializing A, which is the register, to hold the return value to 0 first. And if it is indeed 0, if they match, if I does equal to fan out, in that case, I should return a 0, because this is really just saying, I will return I does not equal to fan out. So JZI means, we should return a 0, which means, don't skip over, putting a 1 into register A. So that is also correct. And if the comparison ends up with the Z flag being cleared, that means A and B are different. In that case, JZI does not happen, and register A, which is specified in return value, gets a value of 1, which is non-zero, and that is also what we wanted to do. And this is the label, just so that we can skip over the LDIA1, and that is at the right place. And then we end the outer conditional statement, and that is correct. And now we add the LVS amount, to register D. That is also correct, except register A cannot be used in this case, because register A is containing the return value, and so we cannot use register A in this case. I'm going to say changed. And register B is fine, because register B is free. So that should address the first subroutine. Okay, that should address SD insert as a subroutine. Now we move on to insert, which is a shorter subroutine. So here's insert, and the first thing we check is how we define the labels. N is a local variable, the only one. And then LVS, local variable size, is N1 plus. That is correct. New node is the first parameter, and it is the number of bytes for the local variables 1 plus. The 1 is for the return address, and that is correct. And then point is the second parameter, and it is right after new node, and new node itself has a size of 1 because it's a pointer. So that is correct as well. So it looks like all of these are correct. And this time we allocate correctly, using sub db to allocate for local variables. And then we check, we initialize n to 0. So here we have the offset address. This is specifying the constant value of 0, put it into whatever b is pointing to, and b is the address of n, so that is going to initialize n to 0. And once again, we have a loop. So with a loop, my usual thing to do is to check to make sure at the end there's an unconditional branch to the beginning. Um, let's check that. All right, so I think we are missing that, right? So if we're missing that, we're going to have to insert it here. So I'm going to say JMPI to insert while begin. And I'm going to write a note here and say this is added so that I can keep track of that. Okay, so now we get back to the beginning and we look at the condition. So the condition is um, it's still calling SD insert, but this one is a little bit easier because all of these are fairly straightforward. So we have to so the order is off, right? Because we should be pushing point first, and this is now changed. Then we push new node, but we also have to remember the 1 plus because it is now 1 byte off from where it used to be because we just pushed something on the stack. So we'll say this is changed, and then we push the first argument last, which is n, and this time it is 2 plus because we got two things pushed on the stack already, so the offsets are all at 2 bytes off at this point. And then we push the return address. Okay. Oh, okay. I better make sure that I do get the value of each one of these. So we have the offset address value. Okay, that's good. We have the offset address value, and there's one additional dereference here. Okay, so we'll say this is now deleted, and then we have the usual push sequence, and then we have the offset address value, and then the push. Okay, so that looks good. I almost did not catch this one. And now we look at the return address. So we specify the return address in register B, decrement the stack pointer stdb, so we push the return address. That looks right. And then we do an unconditional branch to the subroutine. That looks right. Increment D 3 times, okay, to deallocate all 3 arguments that are still sitting on the stack. That is also correct. And AA so that we can check whether A is 0 or not. A is the return value in this case. And if it is 0, we stay in the loop. And that is correct because the condition says while not blah blah blah, which means if it is 0, we stay in the loop, which means if it is non-zero, we get out of the loop. So that looks right to me. In the body of the loop, we're supposed to increment n. So let's check this code. We're getting the offset, we're getting the address, C has the value increments, and then the incremented value gets stored back into n. That looks right to me. This is what we added earlier so that we can get back to the beginning of the loop. So when this is all done, we have the return value specified. Oh, there's no return value needed because this is a void function, so that's good. No need to worry about the use of register A, which is not the case anyway. So we are using register B to deallocate the local variable. So adding the offset is correct to deallocate, and then we have the return sequence here. So that is all good. Now we look into main. Let me look at the time. Okay, I think we got enough time to do this. All right. So now we're in main. Main is pretty easy, right? So main doesn't have a whole lot of code, but it still has a local variable, which is root. So root is a local variable, so the stack pointer should point to it once we do the allocation. And then the amount of bytes to allocate for main for local variables, it's still the same, which is the local variable that has the lowest location. Excuse me, I take it back. It is the it's the last local variable allocated, using that label, and then plus the size of that last local variable. So 1 plus is correct here because it's just a pointer. Sub dd to initialize the stack pointer, and then we do the allocation by subtracting main underscore LVS from the stack pointer. So those are all things to do before we start the first statement, which is this statement here. Root equals to the address of n1. N1 is a global variable, so it is allocated in a static way, and that's why the label itself is the address of n1. We put it into register A. And root, on the other hand, is a local variable, so we do the usual trick of offset address and then store A into wherever B is pointing to. That looks right to me. Now we're moving on to the call to insert. So we have two arguments to push. The first one is the address of root. So we have the offset, this is the address, and then we push it on the stack. That is correct. And then the second one is to push the address of n6 on the stack. N6 is a local variable in C, so that's why the label is the address itself. So we don't need the add BD here. So we comment this out, and then we say this is removed. And then we decrement D, and then we store B to D where D points to. So that is correct. And now we have the usual sequence to call, but it's good to double check. This is specifying the return address in register B. We allocate 1 byte. We store register B to where the stack pointer points to. Yeah, looks right to me. And then we call the subroutine insert. When the subroutine comes back, we need to do to increment D because it has 2 arguments. So this is added. And after that, it is done. Okay, main is supposed to be done, so we deallocate its local variables and we get to the halt instruction. So that should do it. Okay, so now this is completely just reading the C code on the left hand side and reading and correcting the assembly code on the right hand side. I think I caught most, if not all, of the mistakes. I do have the key, but I didn't read the key, okay? Because I don't want to read the key to you. Because otherwise I can just send you the key and I don't have to do all of this stuff here, right? So the idea is to do this interactively. So now you have an option if you have time left, okay? If you don't have time left, you can just turn it in. If you do have time left, one thing you can do is to actually uncomment the C code and run it so that you can find out what the C code is going to do. That's one thing you can do. If you don't want to do that, okay, because you say, okay, but I'm really running out of time, I just want to catch the most obvious stuff, so I can actually check whether the program works or not. That is doable too, although it is not highly recommended. So the question is, what is the C code going to do? And the best thing to check is to single step through the code and kind of follow through the code and find out what it does. You can also just kind of statically analyze the C code, because after you have taken CISP360, you really should be able to read C++ code that is given to you and understand what it is supposed to do. All right, so let me check the time. I still have like a bit of time left, so I'm gonna continue with this, okay, and kind of see whether I can show you how to debug this code. All right, so I'm gonna first extract the C code out. This is line 26, and this is line 50 80. Okay, I cannot remember the first number anymore. So the first one, this is 85, and 26. Okay, it's 26 to line 85. We want to write that to a file. I'm gonna put it as I'll just say final exam or final .c in the parent folder. So this is a new file that is being created. and we're gonna check that out. And the first thing we do is to remove all the initial comments, the two slashes and the space. And now we have the, oh, okay, I forgot about the G. Okay, let me do that one more time. Okay, substitute the initial slash slash followed by a space with nothing, and the G is not really needed here because it only happens once on each line. Much better. Okay, so now we can just kind of look through this code and see what it's going to do. N is just a unsigned integer. If n is 0, if n is non-zero, it will go through this code. If n is indeed 0, then it will go through this code. So if n is non-zero, it will then check whether point is null or not. If point is null, it is going to use point. It will update point so that whatever the pointer that point is pointing to is going to point to new node, and then it's going to return a 1 to basically say yes, uh, we we found a place to put the reference of new node, and otherwise it will return a 0 to basically say nope, the the pointer to the pointer that you gave me is pointing to something that is non-null, which means it's occupied, and therefore I was not able to store new node as a pointer to the pointer that point as a parameter is pointing to. Otherwise, if n is indeed non-zero, okay, then it's going to go through this code. So if n is non-zero, it will basically do a recursive call. As long as I is less than fan out, it's going to basically check every single element of the p member, which is an array of the structure that p is pointing that point is pointing to, until you find a place to stash um, the the pointer of new node, and the increment is really just advancing to the next item in the array. And the return value is whether I equals to fan out or not, because if I does equal to fan out, that means the only reason we could get out of the loop is to fail this condition, which basically means none of the call to SD insert was successful, which means whatever I couldn't find a place to put um, the pointer new node um, in the structure that the pointer that point is pointing to uh, can afford. So I could not find a place to put it. So this is done recursively, which means so when we call it in C, this is insert, which is really just a helper function. So insert is controlling n, and n is the first parameter, and it is basically every time we do the recursion, n decrements by 1. So that part is illustrated here. And this is how we can terminate the recursion, because n is decremented by 1 in each iteration. So the idea is to find out exactly what got changed in the execution of the C code, because it's only calling insert once. Okay, so that means we need to kind of track down, because we want to track down whether this got executed once, and if it does execute it, it does execute um, where that what is pointing to at that point. Okay, no pun intended, but that's what we need to check when we run this code. So since I do have time right now, I'm going to go ahead and debug this code. So we'll use gcc-g-o final.c to compile the C code. It does compile. And then we gdb final. And then we look into SD insert and locate. We put a breakpoint on line 23 because that's probably a good place to check. And then we run the code. Alright, so line 23 we did get to line 23, and now we want to find out, of all the structures, which one got changed. So we have to find out what point is pointing to. It is null, so that's, well, okay, that part is kind of, okay, so we want to find out what is point. All right, so point is n2 plus 16. It is um, somewhere in n2. Okay, and now we can also check the recursion. We can do a backtrace to find out how we got here. This is main calling insert. Insert calls SD insert. SD insert calls SD insert, and this is the last invocation, the most recent invocation of SD insert. So we can see this is level 2, n equals 2, n equals 1, this is n equals 0. And we also know that new node is n6 because we're inserting n6 into the whole thing. And we also know that point is n2 plus 16. So now we want to find out exactly what is n2 plus 16. Okay, so we can print out what is n2, and n2 looks like this. And now we can look at each member, look at the address of each one, and find out which one matches what we want to access. So n2.v has an address of it ends with a 40, and what we're looking at here is ending with a 50. I mean, obviously, I kind of have a pretty good idea of where that is, but we're going to check it, okay, just step by step. So this is n2.p bracket 0. This is the first element of p as a member. It ends with a 48, and the second one is going to be the one that we want. So there we go. So we know that n2.p, or the second element of the array p as a member of n2, is getting changed. So you might want to make a note of this, somewhere, because this is significant. This is how we're going to test the assembly code. So I'm just trying to think of how to make a note of this. Okay, so we are going to put this into my clipboard, get out of this, and then go back to the exam. And I cannot remember where I put it. Oh, okay. There's a subfolder in here that I put everything. And okay, so let me see. Find. It's fx-w0006887 ttpsm. It is in. Oh, maybe I changed the name. Where did I put it? Oh, it probably is still in tree. Oh, new tree, that's it. It's still in. Nope, that's not where it is. Oh, where did I put? Or is it in the folder itself? Oh, it's in the folder here. Okay, so my mistake, because I thought it was somewhere else. It's actually here. So I'm gonna go back into fx-w006. So getting back to this file, and I'm just gonna put some comments down here, and basically paste the thing, and say this is changed, because this is what I can look for in the trace to see whether it is updated. Okay, so now we can go ahead and try to run this code. Okay, let me see what I should do here. I am going to borrow this tab so that we can look at the code. So put this up to the parent folder, and then look at final.c as one, and fx dash my name. I'm looking at the time. Okay, so that's the source, and then I can use this one to go back to, I think pop D may do because I just pushed D. There we go. Back to River Spider, and now we can test this code. All right, so let's go ahead and do that. Um, I probably missed something, but it's worth a try because I got time to do it. The code is good. Okay, so now we are tracing. All right, so now we go back to our trace. And the first thing we need to do is to find out where that byte is supposed to be located. Um, Let me go back to the code so I can show you exactly what I meant. Okay, so in the assembly code, I made a note here. I want to find out where is element 2 of the array P that is a member of N2. So we can find that pretty easily by looking into the assemble tab. So in the assemble tab, we want to, yeah, it's going to look really weird because all the comments are gone. It does not. Comments are basically cleaned before the assemble tab gets the text to assemble. So they are all gone already. So we are looking into N2. This is N2. The first member is a value. The second member is these three are P, and this is the one that we're supposed to have updated. It has an address of 1.5 in assembly language. So that's what we should be looking for, is the update of location 1.5 in the analysis. So we go to analysis, and then we highlight column C, and then we do Control H to look for an update of 1.5. So 1.5 equals 2, and see if it is. Oh, okay, it is changed, and it is supposed to be updated to. Okay, I cannot remember what parameter I used in the C code, so let's check that. Alright, so in the C code, I am supposed to use N6, or the address of N6, to update that location. So now we need to go back to the assemble tab to find out where N6 is, because I'm suspecting N6 is at location 03. That would be nice if that was the case. So we go to the assemble tab, and then we track down N6. So we need to scroll up. This is N6. It is indeed starting at location 03. So at least we got to the same statement that we put a breakpoint in earlier in the C code. So now that is what is left to do in the analysis tab is to go all the way to the end and find out whether the stack is balanced. So to do that, we have to look into summary to find out how many rows we got. 1091. All right, so we go back to analysis. 1000 and what again? 1092 or 93, somewhere like that. Okay, so that's where we ended. Okay, exactly. And the stack pointer is indeed balanced. So everything looks good. Okay. I mean, obviously I could have made some additional mistakes and somehow they cancel each other. There is such a thing called masking. So you can have a bug that will mask another bug. Um, and those are pretty nasty because the bug. So in certain instances, the bug would mask each other, which means it won't show up. But in other situations, it will show up. So it doesn't. It's not very consistent. So I could have a bug like that somewhere that would cause the program to appear to run 100%, perfectly. But it is not very likely, okay? Because in assembly language code, if you make the slightest mistake, you get one instruction wrong, it's going to crash the whole program. So there we go. So for the most part, I shouldn't say that. Not for the most part, I entirely only use the static code in C and the static code in assembly to locate all the problems, and that should be doable. Okay, you just have to be very careful. Just kind of comb through the code carefully. and understand all the concepts, and commenting is going to help. Okay, so once again, I'm going to say, if I don't see any commenting in the assembly code, and yet problems were found and stuff like that, I get a little suspicious, because it's really hard to find bugs, um, without being without tracking what each register has. So that is that. Um, I'm I'm done. I'm done explaining the answer to the final exam. If you do have any questions after watching this video, bring it to the class, um, and I will see you at 5:30.